Alright, hey guys, what's going on? So today we are going to be talking about curvature of plane curves. Sounds a little bit redundant, but we'll see exactly how this works out. Again, if you like this kind of content, please make sure to go on to my Patreon page. Make sure to hit that like and subscribe button as well. That's only if you like this kind of content. If you don't, then do what you will with this kind of information. But anyways, let's get into the topic now. So we are talking about curvature of planes curves, curvature of plane curves, and what we're going to look at is we're going to see how when we parameterize a curve by some sort of function, we'll be able to understand the curvature of that curve in terms of the function itself, and we'll see what exactly that means. So we are going to take an arbitrary curve, and this is the arbitrary curve, this black curve right here. And we really want to understand the curvature at a point. Okay, so we're going to take the point P. We want to understand the curvature at this point P. This is the diameter, right? So this isn't really well drawn out, but this should be the center of the circle. This is the diameter, so the diameter is going to be 2 over K. And we want to, much like when you take a derivative, you take 2 points and then you take the limit as one point gets closer to the other. We're going to take a look at what happens when Q gets closer to P. We want to understand what exactly that means in terms of the curvature. To do that, we start off by considering this picture right here, where we have the x-axis, and we have a circle in which the x-axis is a tangent line to the circle at some point. And that point is going to be P. And a few things we want to note here is that the distance here and the distance here is we're going to take the square of those, the square of this over this, and we're going to see just so what the relationship is between this value here and this value here. So when we do that, well, by Pythagorean theorem, right, this squared plus this squared equals this squared, we get this. And then by simple, just split the denominator split the numerator, right? So this is going to be equal to epsilon squared over epsilon squared plus sigma squared over epsilon squared. We get this, right? Because this is 1. So this is approximately 1 in the event that this right here is really small, right? So we want this to be small. We want epsilon to get really small as we're dragging Q towards P. So what that would mean is that this value, this hypotenuse value squared is equal to this squared, and so we get this relationship. So in order for us to consider infinitesimal distances, we want this condition to be true, right? And so that's to say that the hypotenuse of this triangle, when formed as with P as a point on this triangle, this value here is going to be equal to this value here. Okay. All right. So where does this take us? So the next thing we want to consider, right? So the next thing we want to consider is this value again. We want to look at this triangle now. Okay. So this here is going to be this right here, okay, 2k, or 2 over k, right, that's going to be the diameter here, and then we have sigma to epsilon, right, so sigma is going to be this right here, so this distance right here, okay, so sigma is going to be there. And by argument of similar triangles, you can really just look at this triangle and see how these two triangles, this triangle here and this green triangle here, are the same, or not the same, but they're similar. This is going to be that relationship. And so we can rearrange a few things. When we rearrange a few things, we get this, and then we get down to this point. We can isolate for sigma, and we get that the sigma is 1/2 the curvature times epsilon. So 1/2 of k, right? So K, this should be, get the curvature, times epsilon, all right, squared. Okay, so these are two important things that we want to keep in mind when we do the next thing here, because this here and this here are going to be used in the next derivation process. In the next derivation, we want to take a look at how these functions, right? These functions are going to play a role in sigma. They're going to play a role in a few other things, and they're especially going to play a role in defining curvature, and we're going to get to that. But first, we're starting off from sort of bare bones, right? If you recall from calculus, we have our Taylor approximation. Our Taylor approximation is right here. If we can subtract this from both sides of the equation, we're going to call this sigma, okay? And we're going to see how this sigma is related to this sigma right here eventually. But before we do that, we see this, we get this here. This is going to be 0 if the tangent line is parallel to the x-axis, right? So right now we're saying that it is the x-axis, and so this is going to be 0 because the tangent, right, the derivative at that point is flat, it's constant. We're doing this with respect to an x-axis, and so if it's constant, that derivative is going to be 0. Okay? And so what we get is this right here. Okay? And so we get this, and so therefore our curvature, our curvature is equal to the double derivative of the function, right? The reason for that again is because we have this right here, right? So this right here, this looks very similar to this right here. So sigma, we have the curvature. This should be the curvature. So that's where we're drawing this conclusion from. Okay. So what if the tangent line is not parallel to the x-axis? So if the tangent line is not parallel to the x-axis, well, here's that tangent line again. We're going to deconstruct this picture here, and as we go through this derivation. But what we want to start off with is this brown guy right here. So that's this line right here. So we can think of this as, here's our tangent line, here's the x-axis now. Right, so the x-axis is this green line. Okay, and what we want to do is we want to say, well, this brown here, this brown line here, if this brown line is this guy, then this guy is going to be here. Okay, this distance from A, or from B to Q, or no, actually from A to Q is going to be this guy right here. And that's just really by virtue of this being sigma. These are all similar triangles. I'm not going to go into these proofs, but these triangles scale with each other, essentially. That's what makes them similar triangles. Okay. And so, actually, these are actually similar triangles, this should be, let's see here. This is going to be, this is the hypotenuse right here. This is that distance. Then the cosine should actually be, since it's cosine, that should be the angle, right? Anyways, so if this holds true, then this AQ distance is going to be this. Oh, I think my face is in the way. Going to be this right here. All right, so next if we say that PA is approximately equal to PT, so PA and PT, well, we're saying that this distance here is very small. That's what we're doing right here, okay? And we're going to say that that's equal to epsilon. So that distance epsilon that we talked about here That's the distance between that P and that Q. Right, so here's the P and that Q, here's that distance. So we want to say that this here is epsilon, essentially. That this from P to T is epsilon. And so, if that's epsilon, well, we're saying this is approximately epsilon, right? So PA is approximately epsilon. So that means this distance here is going to be this. Right? Just this is a cosine argument, right? This is the angle. And again, this is epsilon. We're saying that this is essentially equal. What we're saying here is that from P to T is essentially equal to from P to A, and that's epsilon. Okay, that is the approximation that we're making here. Okay, so now we recall the Taylor approximation. Here, this is what we got to last time. We said that this was equal to sigma, but now instead of making this 0, this is the distance from A to B, right? So from A to B, and this distance from A to B, again, so that's right from A to B, because this plus this is going to give us sigma, right? So this plus this is going to give us the sigma value, which is the entire thing, right? So this is a little bit tricky to see, but we said initially that this was this. This is part of that Taylor series, right? This part right here, this is part of the Taylor series. And then this here we said was this. Right, so AB is the first term in that Taylor series, and AQ is the second term in that Taylor series. Okay. And so what we get is that this is AB. So if PB is unit distance, if from here to here is unit distance, then we could say that the cosine of theta, or the angle, the cosine of this, is going to be 1 over 1 plus the f prime squared. And why is that? Why is that? Well, this is f prime. Okay, this was our dx. This was 1. Right, so if I just draw that triangle, this was 1, this is f prime, this is dx, this is sigma. Right, so cosine is going to be opposite, which is 1 over, actually let's see here. Wait, so this, yeah, so this is going to be that triangle, right? And that's where we're getting this from right here. Right, because again, the cosine is the hypotenuse over, let's see here. See, the cosine of theta is the hypotenuse over dx. Oh wait, never mind. I'm not going to go belabor this point too much, but this is the triangle we are looking at, right? And that's again this guy right here. Okay, and so from this triangle we get, so my apologies, the triangle was actually wrong, right? Because we said this was unit distance. If PB has unit distance, then the triangle looks like this, right? So this is point P. We're investigating at point P. This is point B, right? So by Pythagorean theorem, again, then that means the hypotenuse is going to be this. And so the cosine of this is going to be 1 over the hypotenuse, right? So that is where this guy comes from. So let's keep this guy in mind, this guy in mind, and this guy in mind now. Okay. And let's move on. So we're taking 1, 2, and 3, And we get that sigma is now equal to this. And given that we derived our curvature to be equal to this, right? Remember that came from way over here, this guy. And this from the same picture, right? The only difference here is that, again, we did not really need to draw all this extra, the tangent line, and these two extra lines here. This came from Newton's lemma, and that is this right here. So given that we derived this, we get this. Okay, so that the epsilons are really just going to cancel out with each other, and this here, it should be squared, right? Because we have this guy right here. Oops, this guy right here. This is that epsilon, right? Because we said delta x was that epsilon. This is that change in x again. Okay, so what we end up getting is this. Okay, so the curvature, so therefore we can parameterize some path, again with some function, that function being f(x) at p at some point p. And there's a few things to note about this equation. Like, so for example, one, if this is just a constant, then the denominator here is going to be, this is going to end up to be 0, and so the curvature is just going to be this. But if it's just a constant, then the double derivative of a constant is just 0. If f of x equals cx plus b, then we get this, and therefore we have this relationship. Okay, but that's also going to be 0 because, again, the double derivative of this is just going to be 0. If this is this has a square root now in it, or not a square root, but the power to a power of 2 in it, or a polynomial with degree 2, then we start getting curvature because the numerator is no longer going to be 0. Right, so this numerator here, when we take the double derivative of that, that's actually going to be 2cx, right? If well, so the derivative of that is going to be 2cx, and then so the double derivative is going to be 2c. So this is that numerator. Okay, so we actually start getting non-zero values for our curvature when we have anything being above 2, any polynomial with degree 2. If f of x is anything with a power over 2, this is exactly what I said, then k becomes a function of the x, that parameterization. So that's to say that, for example, I was actually doing an example. I actually have an example right here. So f of x, so for example, if f of x was cosine of x, and we want to understand the curvature at pi over 2, then we get these guys right here, right? So the first derivative of sine of x, the second derivative is negative cosine of x. So this is a function of x now, right? Because we have an argument of that depends on the position where you are along that path. That's at x position. And so we get this thing as a function of x. We can plug pi over 2 now into that, and what we get is negative 1. Okay, this is interesting, right? Because if we think about the function, the cosine function, it looks something like this, and this, we're looking at pi over 2, right? So pi over 2 is right here, right? Because we have 0, pi over 2, and then pi, and then 3 pi over 2, and then 2 pi. So we're looking at the curvature at this point right here. Right, so the curvature at that point, we can imagine having a circle at that point with the radius and all this kind of stuff. That this circle is going to help us define. This is how exactly we defined curvature. That we defined curvature in terms of putting a circle along at some point on a curve and then getting a tangent to that curve, and that circle sort of the radius of that circle defined the curvature at that point. Okay, so we went through talking about how we can parameterize curves now with a function, and what we did is we talked about curves. We've talked about curves now in sort of this quantitative way in terms of defining the curves as functions, and we defined how curvature was expressed in terms of these functions. Next, we're going to talk about how we can relate these things now to physics, because that's going to be something of interest. Anyways, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to go on to my Patreon page. Again, if this is the kind of content you're interested in. And with that being said, I'll see you guys in the next video.